Thank you very much for the introduction. I would like to thank the organizers for giving me this opportunity to discuss our recent results in this great meeting for last 10 days, 12 days almost. Okay, so I come from this institute called NISER, National Institute of Science, Education and Research. This is a place in the east coast of the country, and I'll discuss about this re-entrant localization transition in quasi-periodic lattices. Although the meeting is on periodically and quasi-periodically driven system, I'll join the team to apologize again that I'm not going to say anything on this driven system. And the reason is that people have already started working on this driven system where they have seen this re-entrant physics. If you remember, David Weld gave a talk last week where he mentioned about this. Krishnendu Sengupta is author of one paper where they have seen re-entrant localization transition in driven systems. So in that sense, I'm safe. Okay, so it's a fairly new institution, and many people have asked me where I'm from. So I have to mention where exactly I am from. So I am from this place, which is in the East Coast. And this work which I'm going to present is the work done at two different places. Earlier, I was working at IIT Guwahati, which is in the northeastern part of the country. Recently, I moved to this place, so I should acknowledge both these affiliations. So you can find the work I'm going to present in these papers, which are written at both the places. I mean, some are from IIT Guwahati and some are from NISER. And people who are involved in this work are some PhD students. Shilpi, who moved to Germany for postdoc, and he is going to finish soon. Ashirbad, Mrinal is a postdoc in Kolkata. Suman is a postdoc in Germany, and Saurabh is an assistant professor in some university in Northeast. And Saurabh Basu was a colleague at IIT Guwahati. Soumya is a PhD student at NISER, and Bilal is at Bilkent University in Turkey. Okay, so I'll start with this small, very short outline where I'll highlight the physics of localization in quasi-periodic lattices. For some of you, it might be boring because it's a very straightforward or well-known thing. But for the completeness, I'll just highlight these things. And then I'll come to this re-entrant localization transition, and then multiple re-entrant localization transition, and then I will conclude. So these work is based on simple numerical simulation. And I mean, the physics exhibited or which are obtained from some solution, numerical solution of single particle problems. And we'll see what are they. So I'll start from this famous paper of Anderson, where a random disorder in a tight binding system can lead to exponential decay of the wave function, and one gets this metal to insulator transition. It's very well-known fact. But this scaling theory of localization, where this gang of four, they predicted that localization is not possible, the transition is not possible in low dimensions such as 1 and 2 dimension. This is possible only when your system is above 2 dimensions. But subsequent studies by these people, where this model known as Abri and Andre model, which is a very simple one-dimensional model of quasi-periodic lattices, it was predicted that the single particle localization transition can occur at a critical point, which is the self-dual point of this model. And what exactly happens here is that all extended or delocalized state, they go to the localized state by this sharp transition point, which is delta over j equal 2. And this model is a quasi-periodic lattice, and quasi-periodicity defined by this number beta, which is an irrational number. It's a very well-known fact. So all states extended go to all states localized. Okay. So one can quantify this localization transition by computing this participation ratio known as inverse participation ratio, which quantify the degree of localization. And then one can compare this with this normalized participation ratio to distinguish the two phases. One can clearly see that if you plot this average IPR and average NPR together, then you see this sharp transition at 2. And then if you look at this eigenstate superimposed with this inverse participation ratio, you can clearly see a sharp boundary between this 0 IPR and finite IPR. So this is a clear-cut signature of sharp localization transition in this Aubry-Andre model. And experimentally, it was first observed in this cold atoms experiment in the group of Massimo Inguscio, where you can see that this is a BEC atomic cloud when it is released from the trap, and due to this delocalization, I mean, when the states are delocalized, you can see a free expansion of the cloud, indicating transport in the system. But if your disorder strength is very strong, you see that the cloud is localized. So it's a very clear observation of this transition. Furthermore, there are some generalization, and further generalization of this Aubrey-Andre model leads to this interesting physics called the existence of mobility edge. There is no sharp transition. There occurs an intermediate region where you can find both both localized and delocalized states. And it was proposed by various people in early, maybe last decade, and some of them are already here. Jed is sitting here. Shiram was there in the last week. So you can find a very nice review article by Jed, Shiram, Subroto, and others. And what happens here is that if you just generalize this Aubrey-Andre model by introducing some sort of long-range hopping or power law hopping, or you can write this cosine form of the potential by adding certain other cosine forms, then what happens are all extended states, they go to all localized states via this intermediate region, where you find both localized and extended states. Okay, so this is another type of localization transition through this intermediate phase. To observe this, there was a proposal by the group of Das Sharma, where they consider a shallow optical lattice, one-dimensional bichromatic optical lattice is a shallow, because if it is shallow, then particles, the bosons, can actually hop to the next nearest neighbor site. There is a finite chance. Then they propose that if you consider this model, then one can see this transition through this intermediate region. And here is the theory, numerical results. So if you plot this average IPR and NPR for this case, you see that there is, of course, a transition from extended to localized, but through this region where both these quantities are finite. So this is the critical or intermediate region where both IPR and NPR are finite. And if you see this eigenstate numbers superimposed with the IPR, you see that instead of a sharp transition, you see a gradient like this, where there is a region where both extended and localized states survive. Okay, so this is the theoretical prediction. And immediately after this, there was this experimental observation of this fact in the group of Emmanuel Bloch, where they studied the time evolution of this famous quantity known as imbalance, which is widely used in the context of localization. And what do they do? They create this initial state of a kind of a CDW phase, and then they time evolve it. Okay, so if you time evolve, if the states are localized, then this wave functions, this local wave function, they can actually superimpose with each other, and you get imbalance equals to 0. But if the states are localized, then you get finite imbalance. And this is the experimental observation here. If this VD is the disorder strength, if disorder strength is 0, you see that imbalance is vanishing. And if it is large, then imbalance is large and finite. But for intermediate region, this quantity lies somewhere in between. Okay, so there is this theoretical quantity which was also proposed by Das Sharma's group, known as edge density fraction. So if you initiate one particle at the left edge, then you see some finite fraction on the right edge if they are delocalized, and if not, then this quantity will be 0 in the localized phase. But this was experimentally difficult to observe. So what the group of Emmanuel Bloch did, they monitored this expansion dynamics, root mean square displacement, or the radial expansion of the cloud. So this is the initial state. So if it is localized, then there is no spreading. If it is extended, then you have a large spreading, but intermediate state, you have some spreading which is intermediate to these two cases. So if you compare these two quantities here, these are the experimental data, imbalance imbalance as well as this spreading. Then you see that in the delocalized phase, imbalance is 0. It is finite here. On the other hand, E is 0 on the localized phase, and it is finite here. But in the intermediate regime, you have both these quantities finite. So this is a very nice demonstration of intermediate region separating the localized and delocalized phases. Okay, So what we have seen so far, two scenarios. One is a sharp localization transition from all extended to all localized. And this is another scenario where all extended to all localized through this intermediate region. Okay. Okay, so what next? So can we do something else with this? Can we have some other things appearing in the picture? Okay, so to address this, we consider a simple model known as the dimerized lattice. And this is a very famous model because, you just have to make this hopping, nearest neighbor hopping dimerized, which is T1 and T2. T1 is not equal to T2. So this is given like this. And this is a very famous model in the context of topological physics. And this is known as the Schur-Schrieffer-Heeger model, and it exhibits a topological phase transition as a function of hopping dimerization. And delta is this hopping dimerization. If you tune this dimerization strength, so you go from a trivial to topological phase, and topological phase exhibits two zero energy edge modes, and they are localized. Okay, and you can also see this by plotting these amplitudes where these edge states appear. Okay. And but these are not important in the, I'll show that this topological phase transition is not important in this context, but what we do is we just add this Aubrey-Andre potential to this SSH model. So this is my SSH part, this is the dimerized hopping part, and this is the Aubrey-Andre. And because of this dimerization, you have two sublattice sites, and the Aubrey-Andre can be written as independent depending on the two sublattice sites A and B. And this is lambda A, lambda B for two different sublattice sites. And in the limit of T1 equals to T2, lambda A equals to lambda B, you get back to your Aubrey-Andre lattice. Okay. And when T1 is not equal to T2, maybe you don't have this self-duality. So what is the effect of this quasi-periodic disorder in this dimerized lattice? So that's the question. So we explore the effect of lambda in both trivial and non-trivial cases, and then we saw what exactly happening. So when lambda A is equals to lambda B, then we don't see anything surprising. You get this transition from delocalized to localized through this intermediate phase. But the moment you make this lambda and lambda A and lambda B dimerized, staggered, lambda A is equals to minus of lambda B equals to lambda. It's an equal strength. So in every sublattice side, you have plus lambda minus lambda plus lambda minus lambda. And then what we see is this. So this is the phase diagram. And if you look at this diagram, which is plotted as a function of in the plane of lambda and delta, and on z-axis is this quantity eta, which is the product of IPR and NPR logarithmic of this. What this quantity does, it can actually distinguish the intermediate phase from the delocalized and localized phase. So we are worried about separating this part, this blue region, which is the intermediate region. And these dots are actually computed from individual IPR and NPRs. So you can see that if delta is somewhere here, you go from extended to localized through this intermediate region. But the moment you are here in some region here, you see this extended goes to localized again and again to localized region through these two critical points. So you go from extended, intermediate, localized, intermediate, and localized. So this is what is called re-entrant localization transition. So this localization occurs twice in the system as a function of lambda. Okay, and this is the non-dimerization case when delta equals to 1. So you don't see any intermediate region. So you go from extended to localized. And this thing happens on the other side also. This is the trivial side. This is the topological side. But you don't see any difference. Here also on the trivial side also, we see this cusp, which is a re-entrant localization transition. So topology has no role here. I mean, this topology has only the role in the edge state. There is nothing on this localization transition because it's entirely the property of the bulk. Okay, so how do we quantify this? We quantified this by using this IPR and NPR, average IPR and average NPR. So if you plot them together, you can see that here NPR is finite, which is the extended region. Then at this point, both are finite. This is the intermediate region. And this is first localization transition where IPR is finite, NPR is 0. And surprisingly, you get another intermediate region where both these quantities are finite. And then again, the system goes to a localized phase. So these two transitions are two localization transition points. And this tiny bump here in the NPR is not a finite size effect. And we showed that although it is small, it is actually, it survives in the large length limit. So we perform this finite size extrapolation. You can see that this part in the localized region, this quantity actually vanishes in the large length limit. But in this region, these are quite length independent. Okay, so this is not finite size effect. And we concretely established that this is actually an intermediate regime where some of the states are becoming extended again. So here all states are localized, and here some of the localized states are becoming delocalized. So that's the fact. So that can be seen from this figure, where eigenstate index as a function of lambda is plotted, and where the IPR is plotted on top of that. This red color indicates that IPR is 0. So these are all extended states. This is the mobility edge region, and all states localized here in this region. And now you see that at the middle of the spectrum, some of these red states are becoming red, where that means the IPR is becoming, so IPR is becoming 0 here. That means the states are becoming delocalized. So that's the reason you get this tiny bump due to these states at the center, and that gives rise to this intermediate region. Okay. Yeah, so this is the re-entrant localization, and we also plotted for 2 different cuts when there is no re-entrant localization.
Sorry, question.
Yes.
So this so lambda A has to be a minus of lambda B strictly?
Yes.
Otherwise, there's no re-entrant.
Yeah. So you have to have some staggered on-site potential.
Okay.
Yeah. Structures, meaning this parallel lines and all? No, I mean, it's just that some of the states are having less IPR, but they are finite. I mean, you can see that this is deep color, red color thing is IPR 0. Here it is finite. I mean, but yeah, something intriguing here, why these straight lines are coming, but no idea. I mean, yeah. Okay, so we can see that the states for this, you can see this extended, highly extended states goes to localized, and here there is some extended, localized, extended, localized, and so on. So you can see this localization re-entrant pattern here. So we also computed this fractal dimension from this relation. You can see that you go from extended to localized through this intermediate regime, again localized through this intermediate regime, and so on. So we have also verified for the other moments of the fractal dimension. So everything is consistent to our prediction. Okay, so what is the scenario now? The scenario is this: you have all extended to all localized through this intermediate region, then again another all localized phase through this intermediate region. So this is your re-entrant localization transition. So are there other models? I mean, this is a very, I mean, although it is simple, it requires lattice dimerization, like hopping dimerization, then staggered on-site potentials, etc., etc. So are there other simpler models where this can be seen? So the general intuition is that you need to have some dimerization in the lattice, some staggered potential in the lattice. So what next? So what happened? So we consider the very simple model, which is dimerized again. So here this on-site, this nearest neighbor hopping is not dimerized. It's again tight binding lattice. I mean, if you consider this part, this is the simple Aubry-André model. And we just added this simple term, which is on-site staggered potential. And if you, some of you know, this is the model which was considered in the experiment of Immanuel Bloch to create this initial state charge density wave phase. So this is called a super lattice. So they created this 1010 type structure through this lattice. So if you take this delta as plus delta minus delta, so you create this kind of staggeredness in the lattice. And then you add some disorder lattice, and then you created this quasi-periodic potential. This is a kind of some imagination. This is not a true potential for these two combinations. I just added this for visualization. Okay, so what is this? This is the Aubry-André model and the dimerized local energy. So what is the expectation? Expectation is re-entrant transition, and this is what we get. You see, I mean, this phase diagram is much more richer compared to the previous one. And if you look at this point, you see that if you fix your delta at 2 and then you go like this, then you hit this, this is the intermediate region. You go from extended to localized through this region, and then to localize through another region. Okay, so there is another re-entrant localization transition. Here also, if you go like this, you can also hit this tip here, and then this is another re-entrant localization transition. But interestingly, if you fix your disorder strength at lambda at some point like this, 1.5 say, and you change your delta, the strength of this dimerization, then you see that you go from extended to localized again localized, again localized. So 3 localization transitions. So it's called multiple re-entrant localization transition. So I mean, you can actually control the number of localization transition you want. So suppose you are here, you hit this 1 localization transition. At this point, you have 2 localization transition. Here you have 3. There is a nice small cusp here. Here there are 4 transitions, and everything, all these things are happening below this point 2, which is the Aubrey-Andre limit. So if your delta is 0, so this all extended goes to all localized at this point. But all these beautiful things, they happen below this dashed line, which is the Aubrey-Andre limit. Okay. So this is again quantified by all these quantities like average IPR, average NPR, the Shannon entropy. We also verified with gap ratios. So comparing everything, we get this. And also, if you look at the energy spectrum superimposed with this IPR, and if you are somewhere here around 1.8 or so, then you see that all extended. This is the intermediate, all localized. Then some of the states at the middle are becoming delocalized. So that's the reason why we get this spike here. Okay, so how to observe this in the experiment? So possible experimental signatures from the quantum walk, because quantum walk is just a quench dynamics of some initial state, unitary time evolution. It has been very useful in studying dynamical physics of not only single particle picture, but also interacting systems. But here, what one can do is that we just fix a lambda and then vary delta, and then what you expect is that you go from extended to intermediate, localized, and so on. And what you do is you consider some initial state, and this is a single particle picture. So you just initialize a particle at the center of the lattice, and then you time evolve this with respect to this Hamiltonian, which will have some parameters delta. And this is a time independent Hamiltonian, also known as wave packet dynamics. And then we propose some optical lattice where this can be observed. And what you do is that you consider the super lattice along the x direction and one deep lattice along the y direction. If you increase the depth of this lattice along the y direction, then you will get these stripes of 1D chains which are decoupled from each other. I mean, these are lattices along the x direction. And then there are some experimental techniques. I don't know exactly the procedure, but it is followed by, I think Marcus Greiner has this, how to remove those extra particles sitting here, and you just isolate one column like this. So you just isolate these particles which are at the middle. And remember that all these lattices are independent from each other, and then you quench it. You just time evolve this and take the average of all these dynamics. So you have several stripes like this, and take the average information of all these 1D systems, then you see what is happening. So this is the first thing one can obtain. This is the probability evolution. And if you see that if the states are extended and your initial particle is sitting here, and then the spreading is very fast. So the wave function, the wave packet reaches the boundary quite fast. And if you are in the localized phase, then it remains localized to the initial position. These are very strong localized region. This is, I mean, moderately weak localization. But here you see in the intermediate physics phase, there is something interesting happening. Some of the component, they localize, they remain close to the center, and one component moves fast towards the boundary. Okay, so similarly here also, some component moves faster than the central profile, and that is because of the existence of some of the extended states. So due to that, they show this kind of bimodal distribution. Okay, so here also this is intermediate, localized, and so on. So what you can check from here is this root mean square displacement. Again, this is experimentally accessible quantity. So if you plot this with respect to time, and after a long time evolution, you see that for this extended states, it reaches the boundary very fast, it saturates, and localized, there is no saturation, there is no spreading. And somewhere in the intermediate regime, you can see these values are going like this. So if you follow these colors, you can see that you go from 0, this black one, to red, intermediate, then you have this blue, which is localized. then intermediate, then localized, then intermediate, and so on. So there is this re-entrant physics. So if you track this long time evolved values of this, then you can show some features in this. I'll show that in the end. So you can also compute this survival probability, which is also another quantity which can be observed. So if you look at this quantity, which is the probability of finding the particle in a certain range of lattice sites near to the initial position, so you see that this also exhibits a sort of re-entrant feature in the long time dynamics. Okay, so if you just compare these two quantities, P and sigma, you see the nice picture here, where in the extended phase sigma is large. In the localized, it is 0, but on the other side, P is maximum, and then so on and so forth. So if you can experimentally calculate or observe these two quantities, one can clearly see this re-entrant behavior in the lattice, in the experimental setup. Okay, so well, I mean, this was the proposal for experiments in any setup. I mean, I proposed it for optical lattice setup, but recently there is a paper I saw in the archive where some of these similar re-entrant physics has been observed in this photonic lattices, where I mean, I don't know the details of this, but I mean, I can understand a little bit of this. So what they do is that they have these layers of silicon and silica. And they can vary the thickness of this silicon and silica using this quasi-periodic formula. And if you vary this, you can introduce some quasi-periodic thickness in the system, and this will act like some staggered potential, on-site potential for these photons in the lattice in this photonic setup. And this is the experimental observation of their material. Photonic crystal. So this is silicon and this is silica, and they can map this experimental setup to this model, which is this Hamiltonian. You can see that these are nearest neighbor hopping. I mean, of course, this is similar to the earlier one, which is the dimerized lattice, and they also have some next to nearest neighbor hopping in the system. And this is your on-site potential, which they add in every site. And doing this, they observed some sort of re-entrant delocalization in the system. So this is the strength of this thickness, quasi-periodic thickness they are introducing in the model. So this is the experiment. So you can see that this is some excitations they measure in their experiment. So this colorful things is due to the delocalized phase states. And you can see that at some point, all states are becoming localized. And then all of a sudden, some states are becoming delocalized. Okay, I don't know. I mean, in their experimental constraint, they could not, probably they did not go further than this point, 0.8, 0.9 or so. But up to this point, they checked that some of the states are becoming delocalized again. Okay, so and they have a very small system of say 13 slabs or something like this. Okay, so this is one thing. And the other thing, these are something very new, which we haven't published yet. So what we have done is we have examined the data for very strong on-site dimerization. So what happened? So in the picture, in the previous picture, I showed you this diagram where delta was considered up to 3. So if you consider a very strong staggered potential, then what will happen? So if you consider a very strong staggered potential, you can see that this intermediate region becomes narrowed, very, very narrow further and narrows down. And then at some point, you can see that there is a very faint line which connects to the x-axis. So in the limit of delta equals to infinity, this model exhibits a flat band. And this is the natural to expect that there is a localization. And so this line will touch the x-axis. So that means for any finite lambda, you have localization. So that's a natural flat band localization. But somewhere here, for this intermediate values of delta, we see something interesting, which is very similar to your Aubrey-Andre type physics. So if you pick lambda equals to 0.1 and you vary delta, you see that all extended states go to all localized phase states at this sharp transition, which is similar to your Aubrey-Andre physics. So although this is not Aubrey-Andre, it has some self-duality breaking parameter delta, but still you see this sharp transition, which is quite unexpected. Probably it is happening due to some new self-duality appearing in the system. And we confirm this by computing this IPR and NPR. You can see that there is a very sharp transition. This is the IPR, and this is max IPR. And if max IPR is finite and minimum IPR is also finite, that means all states are localized. So we plot maximum IPR and the minimum IPR, both are finite at this point. So that means all states are localized after this point. Similarly, if you plot maximum NPR and minimum NPR, so both are finite here. So you also know that all states are delocalized in this point. So the question is, the idea is that the outcome from here is that even if you have one staggered potential in the system, you can reach a situation where system has another sort of duality, which gives rise to this sharp transition. And this sharp transition also is interesting. I mean, at this, for this Aubrey-Andre potential, we get this butterfly spectrum if you vary this irrational number. But in this case, at the transition point, if you vary this beta, we see this degenerate, close to degenerate state. I mean, in this, you can see that for large delta, these flat bands appear. But if you zoom in these flat bands, you see that you get this butterfly patterns in one of the bands. Okay, and moreover, in each band you see two butterflies. So you can see that two interesting butterflies visible here. The reason is not known to me yet, but these are something very new. And another interesting fact about it is that this transition occurs, it follows a relation delta equals to 1 over lambda. So wherever suppose delta is 100, so you get a transition at 0.01 lambda. So if it is 1000, it is 0.001. So there is a relation followed by this two quantities, lambda and delta, which is delta equals to 1 over lambda. Okay, so just to show you something, some of this recent work, because as I said, re-entrant localization transition has been studied in different models in the literature now, and experimentally it has also been seen in the non-driven system, also in driven systems. And recently, this is a very recent article in Archive, where we showed that if you consider a generalized Aubrey-Andre model and you make this phase complex, so you introduce non-hermiticity in this model through this substitution, here also you see that this system goes from extended to localized to extended through these intermediate phases. So this is actually re-entrant delocalized. So all these delocalized states become delocalized again by crossing these boundaries. Okay, so this is this alpha is the strength here, and H is being varied along this axis. So in the extended range, you see all the spectrum energy values are real. Here it is all states are complex, and so on. So these are the quantitative diagnostics for this transition. And we also showed how they are complex, whether they are true, all of them are real or all of them are complex through this density of states. So this is just to highlight how re-entrant physics can appear in different models. Okay, so I don't have time to go through this, but we have performed some critical analysis of this phase transitions, localization transition by computing or defining this quantity sigma, which can be related to your Ising model magnetization. So which shows this kind of finite to zero transition, and then you define some scaling hypothesis and then perform this crossing and collapse. So we found some exponents associated to this, but these are not so universal, but we show that there is a nice crossing and collapse of the data. And some of these exponents are also identical across the transitions. But the last transition point, which is somewhere here, is not well predicted through this analysis. So you get this very random picture here. Okay, so the summary is we study this localization transition in quasi-periodic dimeral lattice, and we showed that staggered quasi-periodic potential exhibit re-entrant localization transition, and you also get multiple re-entrant transition by introducing a simple on-site staggered potential. And we propose this wave packet dynamics to observe this. So there is a typo here. Observe this relocalization transition. And the next thing one can think of is the effect of interaction to see this re-entrant many body localization transition, which will be definitely something to look for. And so far we have not been very successful because the states which are becoming extended again are very small in number. So adding interaction in a small system and proving this many body relocalization transition is very difficult. And we are also trying to study the, I mean, maybe one can think of trying to study re-entrant localization of these edge states in the many body limit. Thank you very much for your attention.
Awesome. Thank you for that talk. Talk is open for questions. Perhaps questions from students would also be awesome. Yes, go ahead. Not a student, but please.
So you showed this plot for the non-Hermitian case, right? So, and you said that there are regions where there are all real eigenvalues.
Yes.
Do you know similarity transformations which just maps your thing to some Hermitian matrix then?
Similar transformation of this model?
Yeah, I mean, otherwise, how do you explain that these are all real eigenvalues? I mean, maybe it's a naive question.
No, yeah. So I think this model is PT symmetric at some point. And then this PT symmetry, due to this complex number, the PT symmetry is broken. So you get this eigenvalues complex. And then somehow this eigenvalues become, even if this complex number is increasing unidirectionally, but somehow this real eigenspectrum comes back. So I think Ashish can be, I mean, we are still trying to understand this, but yeah, it's a bit intriguing. Yes.
Yeah, so when you say this is PT symmetric, what is the PT operator actually here?
Yeah, no, so what I'm saying is that we're saying that since you are observing some real spectrum in the system, so naturally we expect that it is PT symmetric. So, I mean, one has to examine what is the PT operator and so on. But what is the expectation? Expectation of the system is PT symmetric, and then some PT broken transition occurs at this point, and then you get complex spectrum, and then again the PT is preserved after some time. So that's what is shown here.
Okay, thank you.
I have a quick question. At some point, you referred to the experiment from McBrexton and talked about the photonic realization.
Yes.
Could you comment a little more on other ways that people could photonically realize some of your predictions?
I mean, one easy thing could be this waveguide arrays, where you can create some waveguide in some, I think, I don't know this materials, but then you can assign some photon at some point and then study the propagation in that. But this waveguide has to have this kind of potential. I mean, you have to create this kind of potential.
So,
yeah. So then only, yeah.
Let me crystallize my question a little bit more. Is it all linear optics, or do you also need certain nonlinear components to be explicitly incorporated and interesting kinds of?
It's linear. It's
okay,
linear.
So it's all linear
Yeah.
optics.
So we don't have any nonlinearity now at this point.
And all of these potentials, you think, ought to be realized that way photonically?
Yes.
That's
I mean,
really cool.
yeah. So only thing is that, I mean, if you can introduce this quasi-periodic patterns in this potentials on-site strength, for example, in this case, they have this thickness which defines this quasi-periodicity, thickness of these slabs, which defines this quasi-periodicity in the system. So if you can have some, or in this optical lattice, you add some extra lattice to introduce quasi-periodicity. In the photonic system, if you can introduce that sort of potentials, then it will be straightforward. But there is, I mean, you don't need a strong nonlinearity in the system as such.
Got it. Thank you.
Yeah, so this model is the effective model that they say that defines their experiment. So it's, if you look at this model, so they define the T and N, which is different in different lattices, even and odd lattices. And then, of course, they have this next to nearest neighbor hopping, which is not there in our previous models. But even without this also, I suppose we get this. So
no, but I'm talking about the EIJ term. So
Yeah.
Ej is it staggered? I mean,
Yeah, so you see, I mean, if you, so the J goes from A to B. So for two different sublattices, you have two different potentials.
I see, and they are really opposite of each other.
That one cannot say, but see,
Because something I'm not clear is why is it so sensitive? I mean, you said lambda A has to be equal to minus lambda B.
you can make it large lambda, small lambda also.
Okay, so they don't need to be minus.
No. It's had to be different.
It has to be different. Okay, thanks.
Some like the lattice sizes you have are sometimes quite strange, 17711 and 4181.
Yeah,
and
yeah.
is that
Fibonacci numbers.
and what happens so it's something special happens at those numbers, is it?
No.
Look at
I mean, that's the maximum limit we have considered. So we have gone up to 30,000 and above. So these are some typical numbers I have shown here.
but like at least in transport and all, there's some special numbers at which you get.
No, these are to create this quasi-periodicity. We compute, we consider these Fibonacci numbers, and in the large length limit, so you approach this beta, this golden ratio,
Right, yeah,
golden
yeah.
mean. So that's the motivation. So all these calculations are done with Fibonacci number side.
Okay. No, I mean in transport at least what you see is that some special numbers there's
Okay,
a jump in the
I see. No, I mean, I
conductivity.
have no idea about that. But these are only, the motivation is just to keep Fibonacci numbers in the calculation. Yes.
So I was wondering, are there any critical exponents for this kind of re-entrant transitions?
Yeah,
Have you
so
explored
they
that?
showed here in the last slide. So if you see, that's nice crossing and collapse with this two length dependent function, which you can define from this sigmas. And at the critical point, they should all cross at this point. So you can see that crossing nicely. And if you follow this critical point and these exponents, and you get this scaling and collapse here. And this nu comes up to be 1.8 or 1.7 something, very close to each other, which is, I don't think in which universality class they fall. But yeah, so there is, one can have some nice scaling and collapse, and one can define these critical exponents and define some hyperscaling law and so on. But these three critical points, because we have four here, one here, one here, one here, one here. So out of these four, we clearly found three critical points behaving properly, but the other one is something very unusual. So we don't have any concrete idea why it is. Maybe there are some multifractal states or something.
And for this, calculating this dependence on L, you probably have to take special L's because it's quasi-periodic.
Yeah,
something
that's
like
what
that.
I said. I mean, you have to take this Fibonacci sequence and various different lengths. Yes.
Awesome. All right. Thank you so much.
Thank you very much.